Hi, my name is Andy Williams, and this is my Lab 3 for physics. So in this lab, we're going to be dealing a little bit with black holes, so I thought I'd give you a little bit of a background. First, black hole is a region of space having a gravitational field so intense that no light or radiation can escape. That's kind of why they call it a black hole. Now, there's one theory out there that suggests that there's huge black holes right at the center of all these galaxies, including our own, and that one day they might just absorb everything. So that's pretty scary, but we don't have to worry about that for a while, so that's good. And lastly, I saw this on a TV show, and I thought it was really interesting, that at some year way in the distant future, we might be able to use man-made black holes to propel vehicles faster than the speed of light, and that would be awesome. But now to get to the lab. So the purpose of this lab was to observe the motion of a star and use that data to calculate the mass of a black hole. The motion of the star was observed by using a CSV file that was given to us. VIDLE was then employed with momentum physics principles to map the motion of the star as well as calculate the mass of the black hole. After running the proper code, the mass of the black hole came out to be about 2.38 times 10 to the 31st kilograms. So both Newton's gravitational law and the momentum principle were used in this lab and applied to the code. The gravitational law gives us the attractive force between any two objects with mass. This situation in particular allows us to set up the equation to calculate m2, the mass of the black hole. The momentum principle tells us that F net equals the change in momentum divided by the change in time. The equation can also be broken down into its parallel and perpendicular components, which will be very useful later for the code. So now let's take a look at some of that code. The initial conditions were provided and are included at the beginning of the code, and that includes a mass for the star, a delta t, and all of this down here. The first while loop is used to calculate the velocity of the star as it travels around the black hole. So now let's look at some of the code that's really important for this lab. So first, the initial and final velocity are defined right here at the top. So now using this, we can calculate the initial and the final position by multiplying the star mass by the initial velocity and the final velocity. Now we can calculate delta V and delta P from this data by just simple math subtracting the final velocity from the initial velocity and the final momentum from the initial momentum. Now dp dt equals to delta P divided by delta T. So according to Newton, dp dt equals F net. Now p hat tells us the direction of the momentum. Now the magnitude of the parallel momentum, shown here, equals the change in the momentum's magnitude divided by the change in time. And then when we multiply by p hat to give it direction, that's the F net parallel component. The perpendicular component is found by subtracting dp dt parallel from the total dp dt. This gives us the F net perpendicular component. So using all of this information, I was able to calculate the mass of the black hole by using Newton's universal law of gravitation, where we have m2 is the mass of the black hole. So this information went into the equation in order to calculate for the mass of the black hole, and that came out to be about 2.38 times 10 to the 31st kilograms. So now let's answer some of the posed questions. The first one asks us to compare the different components, parallel, perpendicular, and total F net, to the parallel and perpendicular dp over dt. And how are they different? So my simple response would be that F net is calculated while dp dt is observed. The difference between them is more how they are viewed. F net describes the sums of all the pushes and pulls, while dp dt is an observation. The fact that they are equal is not as much mathematical, but more an observation. Another way to look at it is that dp dt never affects the object's motion, but the F net does. Okay, and now for the, back here. So secondly, for the second question, asks us if the mass of the black hole was to be switched with another, but the other conditions were to remain the same, would you know that the mass is the same, or would the mass change? And the answer is no, the mass would not change. It would be the same as the original because the other conditions stay the same, and the universal gravity constant tells us that in all the situations, the mass is going to be the same of the black hole. Thank you very much.